systems graphically, okay, solving it by graphing. It actually matches up with section 8.1 in the textbook if you're interested. The first thing here with the cell phone plans, basically what you did is you said minutes used 0, 10, 20, and so on, and you found the cost. I'm not going to go through and fill the whole thing out, but what you should have ended up finding is that plan A, 25 cents per minute with no fee at the beginning, you use 0 minutes, you pay 0, right? But then if you use 10 minutes, how much you pay? $2.50, right? And this is $5, and it goes up, right, pretty quickly. Whereas this one, you use 0 minutes, you're still paying $10. Even if you don't use the minutes, you're paying $10 as your fee for the month. But then it only goes up 10 minutes, you're only paying $11, right? 20 minutes, 12, 30 minutes. So eventually you find somewhere in here, this one catches up to the other one. What this situation means on the graph here, if you try to draw a graph for this thing, the one that's 25 cents a minute with no fee starts at the beginning, but it'll go up pretty steep. I'm not doing a very good job of graphing this. Whereas the other one starts at 10 and goes up like that. And somewhere there's a crossing point. That's the solution to the system. What is the significance of that in the situation here? What's the significance of the crossing point here? I didn't, again, draw it very well, but what does the crossing point mean here? And I think it happens at 65, doesn't it? It happens at a point that's not in the table, but I think for 65 it's the same cost. That's what it is. Crossing point is where the cost is equal. One starts out low but goes up really quickly. One starts out higher but doesn't rise as quickly. The crossing point's where they have the same cost. So if you use a lot of minutes, it's better to be on this plan. If you don't use very many minutes at all, it's better to be on this plan. If you hardly ever talk on your phone, it's not good to have an iPhone plan that costs $60 a month. It's better to have one of those pay-as-you-go phones that cost like 30 cents a minute or 20 cents a text. Because if you don't use it, most months you're not really going to pay anything, right? Anyways, the system that if you tried to write the equations here, if you're using C for cost and N for number of minutes, one of them is 25 cents times the number of minutes. The other one is 10 cents times the number of minutes, but you got the additional $10. If you're trying to write an equation, that's what it is. This is the tough thing in this unit, and we're going to work at it throughout, so don't feel bad if you weren't able to do that. The focus of the first section is doing this, solving a system by creating a graph. The first example I didn't have you do here, you can look at the textbook, and we already wrote down some of the important ideas on the first page. If you copy those notes down, you're probably fine. For this second example here, this is a system, two equations with two unknowns. The hint here is helping you know how you could graph those. The simplest way to graph those is, well, it's not that hard to change them into slope-intercept form. If you're going to change those into slope-intercept form, the easiest thing is to move the 2x to the other side. That gives you y equals negative 2x plus 2. If you're going to graph negative 2x plus 2, start at the y-intercept, which is 2, and then go 1 over 2 down, 1 over 2 down, and so on like that, right? It's better to go far away here to put another dot to draw the thing. Okay, if you're trying to draw that thing for yourself, so the line looks something like this, right? Maybe. If I'm lucky, I can get the line in the right place. More or less, that's the line, except I didn't extend it, but that's okay. The other one, if you're putting it in slope-intercept form, I would put the y over here, and I put the 7 on that side. X minus 7 equals y. X minus 7 equals y, that's like 1x, a slope of 1. Start at minus 7, and go up, 1 over 1 up, 1 over 1 up. If you do that, you get that it's going to cross right here, I think, if I was to do this nicely. It should look something like that. Here's a crossing point. I didn't ask you to write this down anywhere, but the intersection point is the solution. The solution to this system is, what are the coordinates of that point? 3, negative 4, right? 3, negative 4. The solution is 3, negative 4. That's what you're looking for here. That's the pair of numbers that works in both equations. I'm going to assume that you can do it using the calculator. If you can't, it's not a big deal. It's another option for solving it. If you have a graphing calculator and you're on the calculator section of the exam, you're welcome to use a calculator if you want. Okay? This is the thing that'd be important to understand how to do here, is to check your answer. Some of you didn't seem like you were sure of what that meant. Verifying something, what does it mean to verify something? What does the word verify mean? If you're talking about verifying something, can you verify that answer? Check, see if it's right. Okay, verify means to check, so other way to say it is to check. If you think you found that the solution is 3, negative 4, and you know the two equations are, whatever they were up here, 2x plus y is 2, x minus y is 7, 2x plus 2, y equals, no, what was it, 2x plus y equals 2? Forgot already. 2x plus y is 2, and x minus y is 7. I'm going to write them both down here like this. If you want to check to see if this works, just take this number and put it in, right? If you think that pair of numbers works in both, just put it in, right? Put in 3 there, negative 4 there, and see if it works. 2 times negative 3 plus that equals 2. Just put the numbers in, right? 2 times 3 plus negative 4. Does that work? See if it works. Just kind of keep the equal sign there and see if it equals 2. 6 plus negative 4, is that 2? 2 is 2. It works, right? Left side equals right side. Okay, that number works. So it works in that equation. If you want to check the other one, just put the two numbers in. 3, negative 4 there. Copy the rest of it down. Does that equal 7? 3 minus negative 4 is like 3 plus 4. 7 equals 7. It works there too, right? The two sides are equal. If it works in both equations, it's the solution. This is the solution. It works in both. Works in both. Therefore, it's the solution. Okay, if you put the numbers in and check, that's a way of seeing if it's a solution. If you're already given or you found the solution you want to check, just test it in there. That's what the second, or actually the third, example 3 does here. Example 3 is just asking if you know how to check and answer. So it says, for this system, this guy has solved it and found this, Guy, I guess. He's found that that's the solution. You can check it just by substituting it in, right? Substitute that in for x and y. Make that x, make that y. So just do the same thing here, right? If you take this and you put the numbers in, so if you think that this is 2 and this is negative 5, just do the rest of it here and see if it works. Just follow it down and see if it equals 12. 2 minus negative 10, 2 plus 10 is 12, right? It works in that one. Try the other one here. 3x minus 2y equals 4. If you try those numbers in there, so if you try 2, negative 5 there, and you're trying to see if they work, just work out the rest of it here, right? Does that equal 4? 6 minus negative 10. 6 plus 10, in other words. That definitely does not equal. Okay, this is not equal, right? Really, this should say not equal all the way down, or a question mark. This doesn't work, right? Doesn't work in both. Okay, it doesn't work in both, therefore not the solution. Has to work in both to be the solution. If you want it to be the solution, it has to work in both. It says explain what it would look like on a graph. If you drew a graph of this, let's just pretend we drew a graph. I'm just going to do this right here. This is a very small graph. Let's pretend that we drew the first line on here, and the first line had like it went from here to here or something like that. Let's pretend that was the first line. And let's pretend the second line looked something like this. There and here. Where would this point be? Where would this point be in terms of those two lines? Where would it be? Would it be right here? That's very tiny, isn't it? How about if we make a bigger graph than that over here? Where would that be? Here, let's go this way. Would it be, if it works in one equation, where would you find it on that graph? Would you find it out here in the middle of nowhere, not on either line? Would you find it as the intersection point right here? No, where would you find it? Where would you find it? Are you answering the question? Okay, hang on 2 seconds here. It's not going to be the intersection point. It's not going to be in the middle of nowhere. If it works on one of the lines, it's going to be on one of the lines. It's going to be here or something like that, right? Except it's not, right? Wherever 2, -5 was, it's going to be here. It's going to be on one line but not the other, right? If it works in one equation but not the other, it's going to be on one line but not the other. What was your question? What was your question? Sure, yeah, we can do that in a second. There's a couple here. I'm expecting that one of these is going to be the solution. It's going to work in both, and one of them it's not. The only other thing in this section, the last thing here, solve a problem involving a linear system. Here you can do this a couple different ways. You can do it by writing equations, or you can do it just by realizing these are like x and y intercepts, these points. Starting, ending, that kind of thing. And you can see where they cross. I'll leave you to do that one. For this, I guess we might as well really quickly look at this right now. This tram that goes up Grouse Mountain travels from 300 meters up to 1,100 meters. The grid's already set up here for you. If you're going from 300 meters up to 1,100 meters, there's also another tram, a smaller one that takes 8 minutes to go from the top to the bottom. Okay, if the red tram starts at the top, it starts at 1,100 meters. Let's you do color coordinated here. This starts at the top and ends at the bottom, which was, what's the altitude at the bottom? 300. So, and how long did it take? I think the red one, didn't it say the red one is faster? Red one's faster, 5 minutes. So 5 minutes later, this is there. The blue one goes slower, and it says the blue one starts at the bottom, right? Blue starts at the base, so it starts here and goes up to here, but it takes 8 minutes. So it goes to there, right? If I'm joining these points here, this one goes like this. You don't even need to write equations here because you have 2 points. As long as you have points on each line, you don't need an equation. It only takes 2 points to draw where the line should be. I think I kind of blew it on drawing that line. Let me try again. I blew it on drawing the line again, but I think you get the idea. And you can copy this down. I hope you have something down here to go with. Okay, well that's more or less okay, I guess. The red one goes down, and then obviously the 2 lines cross at some point. What's the significance of those, if I was to do this properly here? What's the significance of those, of that point where they cross? What happens at the crossing point? I think I didn't do a great job, but it's somewhere in here, right? What happens at that point? What does this represent? The intersection, what does it represent on terms of the trams going up and down the mountain? What would happen there? That's where they cross, right? One tram's going up, one's going down. That's where they're at the same height at the same time, right? Same height, same time. I don't know what this actually is. Intersect at, I'm going to say approximately here because it probably isn't that they intersect at exactly something. It looks like approximately 3 minutes at approximately 600 and something meters. Okay, 3 minutes, 600 meters. The meaning of the crossing point is when they pass each other, right? Pass each other. Okay, that's where they pass each other. In other words, when they're at the same, like they're at the same height at the same time. It's the only time on here where they're at the same height at same time, right? That makes sense to you? Okay. That is actually, I was hoping we could start talking about section 2. We might just have to motor through it next time. I'm going to give you a little quick introduction to it here. And we're going to just have to keep pushing forward. You might have to do some outside of class. You're going to have to decide for the next 3 weeks. You got homework for yourself.